Page 8 of math induction. So we have the first problem, which is 7c. If a sequence is defined by u1 equals 2 and un equals that for all n that is positive integers, then u subscript n is equal to 2 to the 2n, 2 to the 2 minus n divided by n factorial. So the proposition is this, okay? So you want to write that down. And the base case would be for n equals 1, right? So if n equals 1, then the term is equal to 2, and that would be the left-hand side from here, right? We don't really need this part. And then we're going to use the explicit equation to recalculate. So the right-hand side would be u1 equals 2 to the 2 minus 1 divided by 1 factorial. So that would be 2 to the first divided by 1, which is 2. So they are equal to each other. So p subscript 1 is true. Now we're going to assume that the kth case is true. So basically, we are going to say that u subscript k is equal to 2 to the 2 minus k divided by k factorial. So we're going to assume that is true. Now we're going to take the k plus first case. So we're going to say, we're going to use this side, right? U of k plus 1 is equal to u of k divided by 2 k plus 1. Now we're going to try to manipulate this until we get the next version of this, the k plus 1th version of this. So what our goal is to find this, just to say what our goal is, okay? I'm just going to put in parentheses because this is not part of the proof. Just kind of figuring out where we're supposed to be. We want to get this, okay? All right. And in the process, we want to substitute in this into here, okay? All right. So first thing, oh, looks like we can already substitute that in because on top we have u subscript k. So let's substitute in the yellow part. And then we'll put 2 and k plus 1. And you can see that like the bottom part, it already becomes k plus 1 factorial because you got k plus 1 times k factorial, which is k plus 1 factorial, right? So we got that. Then we have 2 on the bottom, and we have 2 to the 2 minus k on top. Isn't that equal to 2 to the 2 minus k minus 1? It is, right? Because we divide, we combine this with this. That will give us 2 to the 2 minus k minus 1. So let's just rewrite that. We'll write it as 2 to the minus k plus 1 divided by k plus 1 factorial. And that's exactly what we wanted to get. Look at it, it's right there. So we've done the proof already. That was easy. So here we could say that, okay, u of k plus 1 is indeed equal to 2 to the 2 minus k plus 1 divided by k plus 1 factorial if u to the k is equal to 2 to the 2 minus k divided by k factorial. And since p subscript 1 is true and pk plus 1 is true whenever p of k true, then p of n is true for n is greater than or equal to, or we're just going to write n is a positive integer. Okay? All right. Number 9. So for number 9, they didn't actually complete the conjecture. They gave us a sequence defined by a recursive formula. In part A, they say, try to find an explicit, or like try to propose a explicit formula for u subscript n for these integers, okay, 2, 3, 4. So what they're saying is, okay, go ahead and use the recursive formula to figure out U2, U3, U4, and then try to propose the explicit formula. So let's see, U1 is 1/3. And U2 is equal to, we're going to use this formula and the fact that U1 is 1/3. So UN is 1/3 plus, so in this case, N is going to be 1 because we're doing U2. It's a recursive formula. So 2N plus 1 would be 3. And 2N plus 3 would be 5. So we got 1/3 plus 1/15 equals a common denominator. That would be 5/15 plus 1/15, which is equal to 6/15. Now, if we're going to find U3, then we would take U2, 6/15, and we would add it to 1 over, this time we're using n equals 2, so that would be 5 times 7. So that would be 6/15 plus 1/35. The common denominator there would be 105, so it would be 105. Is that right? Yes. So how many times does 15 go into 105? Like 7 times. So 42 105ths plus 3 105ths. So it'd be 45 divided by 105. You could have a common factor of 5 in this case, so it'd be 9 21sts, and that's equal to 3/7. Okay, so now maybe we could, whoops, okay. Go to U4, because U4 is the last one we're supposed to do. U4 is equal to 3/7 plus 1 over, and this time we're going to put 3 in for n, so it would be 2 times 3 is plus 1, which is 7, and 9. So that would be 3/7 plus 1 over 63, which is equal to, common denominator would be 27 63rds plus 1 63rd, which is equal to 28 63rds. Okay, and there's a common factor there, 7, so we could put 4 over 9. Okay, so basically we got 6/15. Oh, 6/15 is reducible too, right? 2/5. Okay, so we got 1/3, 2/5, 3/7, and 4/9. So there's a pattern there, right? 1/3, 2/5, 3/7, 4/9. So the top looks like it's basically, is that the n value or the n plus 1 value? It's the n plus 1 value, right? N plus 1. That's the n. Yes, no, it's the n value. So the top is the n value, and the bottom is an odd number related to the n value. It would be 2n plus 1 value. Yeah, that works, right? So this is my proposal. My proposal, or my proposition, is that there's an explicit formula, un equals n divided by 2n plus 1, which would describe the sequence. So we got the proof. We're going to do the following. We're going to say, okay, p subscript n, I'm going to give a different color here, p subscript n is equal to, a sequence is defined by this, blah, 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 and it's got this for an explicit formula. So that is my p subscript n, okay? And it's for all positive integers. So let's try to prove that true. So if n equals 1, then we'll say that u1 is equal to 1/3, which we know from here. So that's the left-hand side. And the right-hand side, we're going to calculate u1 using this formula. So it would be 1 divided by 2 times 1 plus 1, which would be 1/3 also. So it would be 1 divided by 2 times 1 plus 1, which is also 1/3. That's the right-hand side. So we've shown that p subscript 1 is true. Okay? Now we're going to assume that p of k is true. And p of k is just substituting the n's for k's here. So it would be u subscript k is equal to k divided by 2k plus 1. Okay. Then we're going to take the p of k plus 1 statement, the left side of it, and we're going to try to see if we can make that into the equivalent p of k statement. So like, for example, we know that we're assuming that this is true. Now, I'm going to put this in parentheses, but our goal is to show that u of k plus 1 is equal to k plus 1 divided by 2 of k plus 1 plus 1. Okay, we're going to try to prove that, okay? But the way we do that is we are going to start with the left side, which is this statement here, u of n plus 1 over 2, oh, I'm sorry, this is k. We're going to substitute k's in for the n's, right? 2 of k plus 1 times 2 of k plus 3. So we start out with this, and then we can substitute this into here. K divided by 2k plus 1, yuck. 2k plus 1 plus 1 over 2k plus 1 times 2k plus 3. Do you see how we have a common denominator here? We got this and this. They kind of look like half of a common denominator. Now we just need to multiply the left side by 2k plus 3 on the top and the bottom. Then we'll get k times 2k plus 3. And this will be 2k plus 1 times 2k plus 3 plus 1 over, and we got the same common denominator there. Let's try to shrink this down a little bit so that it all fits nice. Okay. Now we can add the numerators. So k times 2k plus 3 plus 1 divided by, and on the bottom we have our common denominator. Remember that we're trying to get to here. Are we close to that? Let's see. This is basically equal to k plus 1 on top and 2k plus 3 on the bottom. That gives me a goal. So like I want to keep that. And I want to get rid of that. So can I arrange the top so that that's factored out with 2k plus 3? Let's multiply out the top and see what we get. We get 2k squared plus 3k plus 1 on top. And the bottom continues to be 2k plus 1 times 2k plus 3. Let's factor the top. If we factor the top, we'll have 2k plus 1 times k plus 1. Does that work? 1k? That works. Ooh, yuck. I already have terrible writing. I start writing with this inflatable ball pen or whatever, you know, these terrible pens for iPad, old iPads, and it looks even worse. I did it. Okay, so I got my goal, which is to prove that. So it's done. Thus, come on iPad. Okay. So here I'm going to put down that I did indeed prove that uk plus 1 equals k plus 1 over 2k plus 1 plus 1. And it's true if u of k, if I assume that u of k equals k divided by 2k plus 1. And since P1 is true and pk plus 1 is true, whenever pk true, then P of n is true for n is positive integers. Okay, and that's it for this page.